talking about atomic structure, the two things that we really tend to care about is that your nucleus is going to have all the protons. So this guy is positive. And then your electrons are going to be somewhere in kind of a cloud on the outside traveling around. So you're going to have electrons on the outside. So if you just always think about negative is attracted to positive, electrons are attracted to the nucleus, what would affect that attraction? The more protons I have, the more attracted an electron is going to be to the protons. The farther away an electron is, so we know these guys are moving around. The farther away they are from the nucleus, the less attracted an electron is going to be. And every atom has many electrons. We often talk about the size of the atom, and the size is going to be what area would we need to say that this atom is, when we're talking about size, think about how far away are these electrons getting. And when we're looking at how easy is it to remove an electron, we're always talking about the outermost. Because if I want to take an electron away from this atom, it's going to be an electron that's out here. It's not going to be an electron that's closest to the nucleus. And we'll see that electrons have places where they reside. They have s orbitals, p orbitals, d orbitals, f. We're going to focus on s, p, and d for the most part. So when you have an atom, the most stable place for the electrons to go is going to be, if this is the nucleus, the electrons want to be close to that nucleus. So your electrons are going to be traveling around and staying very close. So the first orbital that's formed, the most stable orbital, is going to be the s. And the s orbital is shaped like a sphere. It's the most stable. This one has the electron spending the most time close to the nucleus as possible. The next orbitals are going to be, if this is the nucleus, the p orbitals kind of trace a peanut shape. So the p's are peanut shaped, and the electrons are traveling around like this. There's going to be 3 peanuts. So there's going to be a peanut going up and down, so along your y-axis. You're going to have a p going back and forth, so along your x-axis. And then you would have one coming straight out at you. So along, that'll be my z-axis. So you're going to have 3 shells that are going to have kind of this 3-dimensional arrangement. And the reason they form that shape is that this is the way that they can spend the most time being as close to the nucleus as possible, but not running into each other. Because all these electrons are negative, so they repel each other. They want to stay away from each other. They need their own space, so they form these orbitals. And it's where you're going to, an orbital is, where am I going to find this electron 99% of the time? So we've got the s, then we have the p. So the most stable, the second most stable, and then we have the d. The d orbitals are going to have, there's a few shapes, so let's see. You're going to have these guys that are going to trace like this, and then you can rotate that around. You're also going to have orbitals that are going to go in between the axis. And there's going to be 4 of these guys. And then there's going to be one where it's shaped like a pea, like a peanut, and then there's a donut around. So with the D's, with the D orbitals, quite often people, we only come up with these things so we can help remember. S is shaped like a sphere, P is shaped like a peanut. The D's are going to be shaped like 4 flowers in a donut. And that's the donut, this guy. Okay, so you're going to have 4 that are shaped like that. The orbitals are just rotating around in different regions, and that guy. So that's how the electrons arrange themselves so they can be as close to the nucleus as possible, but still stay away from each other, still have their own territory. Most stable because it's the closest to the nucleus, the second most stable, and these guys end up being a little bit further out. Alright, so when we're trying to describe where electrons are, that's when we're using this thing, this electron configuration. So maybe you remember from Gen Chem when you would say 1s2, 2s2, 2p6. When we read this, what it's saying is, you're going to put electrons on the first shell of an atom first. The first shell is going to be the closest to the nucleus. And once you filled up the first shell, you start to fill the second and the third. So this is saying on the first shell, in an s orbital, we have 2 electrons. On the second shell, there's an s orbital and a p orbital. So the s orbital has 2 electrons, the p has 6. And then in the third orbital of the atom that is being described by this electron configuration, there's 2 electrons in the s orbital. So let's see how this relates to the periodic table. When you did these in Gen Chem, it's so repetitive that you end up memorizing, but you don't need to because you probably forgot if you're not taking AP Chem. It comes straight off of the periodic table. So these numbers right here are talking about, am I on the first period? So am I on this first period going across? Am I talking about hydrogen and helium, where the electrons go first in the first and second spot? Am I on the second period? So am I talking about this S and this P? So that would be that 2 and that 2, and then this 3 back describing these guys. Okay. The letters are talking about the orbitals, and the orbitals also are shown in the arrangement of the periodic table. So these first 2 columns, the alkaline metals, these are your s orbitals. So they fill first, so they're the most stable. Then the next guys you're going to have going from here to here, and we assume that we put the helium over here when we're filling it in. This is going to be your P region. And then from here to here, all your Ds, well, your transition metals, those are your Ds. And then transition metals are your Fs. I think the hardest thing for kids when they're filling these in, by the way, is they'll wonder, well, which comes next? If you follow the atomic number, you'll always know which comes next. So that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'm at 11, 12. You just keep following. Where it gets a little messy is down here. 55, 56. This 57, go ahead and put it here. We'll go 57 through 70. And then we come back up and we'll go 71 and on to 86, 87, 88. Go ahead and take this 89, we're putting it here. Fill these guys in, there's 14 of them. Come back up here, finish this. Okay. So the 1 tells you if you're on the first shell, second shell, third shell. So this is your principal number, what shell am I on? This next one is subshell. Subshell is what type of orbital. So are you in the S? You know, are you in this guy? Are you in P region over here? Are you in the D? Then the last thing, these guys are telling you how many electrons go in each of those subshells. So this is saying on the first period in the S subshell there's 2 electrons. So the first one goes here, second one goes here. So we said helium would be over here. Then on the second energy level, in the S subshell, there's 2 electrons. So 1 here, 1 here. And then you continue on the second energy level, and you're in the P subshell, and you fit 6 electrons. 1, 2, 3, 4, 5, 6. 6 electrons fit in those 3 P orbitals. And once you've done that, now you're on the third subshell. You're in the S region, you can fit 2 electrons. So what we're doing, what we're describing is you have your nucleus, and you're saying where you're going to put the electrons. So this is a Bohr model. Bohr is where you show the electrons, the electron shells. So this thing is going to have 3 shells. First, second, third. And this has 3 shells when it's in its ground state, when the electrons aren't excited and jump up. So it's saying on that first, it's going to be in an S, there's going to be 2 electrons. You can say, switch colors. Here's 2 electrons. Okay, and then in the second shell, there's going to be 2 electrons in the S, 2 in the P. They all look the same on the Bohr model. Bohr doesn't really distinguish between S and P in their shells. Just put them on there. And then the 3S, it's going to have 2. I'm going to put them on one here, because electrons are, they tend to split and then pair, just so this thing would make, it would lose its 2 valence electrons actually because it's a metal, but we'll look at number of valence electrons to figure out how many bonds it can form. Okay, so what this does is this describes where electrons would be for an atom. So an atom that has this many electrons would have its electrons arranged like that. Okay, let's try a couple. For selenium, I'm going to erase this because I cannot read my periodic table. Selenium is right here. So we're going to describe 34 electrons. I'm going to start with, I'm in the first shell, and I'm in the S region, and I'm going to fit 2 electrons, 1, 2. Let's put that back, I liked that. 2 electrons, so there's 2 of my 34. Now I'm down to here where it says 3. So I'm in the second shell, I'm in the S region, and I can fit 2 electrons, so 2s2. 3, 4, I go over to here, atomic number 5, so now I'm in the second shell still. I'm in the P region, and I can fit 6 electrons, because there's 1, 2, 3, 4, 5, 6. So 2p6. From there, I jump down to here. Now I'm on the third shell, S region, 2 electrons fit, 3s2. I've described 12 electrons, now I'm on to 13. Still in the third shell. I'm in the P region and I can fit 6 electrons. So I'm down to here, 18, 19. Now I'm on the fourth shell, 1, 2, 3, 4. I'm in the S region and I can fit 2 electrons, 4s2. After that, there's one little tricky thing that happens. The S's and the P's are on the correct shell for what row they are on the periodic table, for what row they're on the periodic table. The D's are going to be one behind. So this is the first shell all the way across, this is second, this is third. This is the fourth here, but this is the 3D here. So the D's are behind. Then we're back to 4P. And this is going to be the fifth shell, but the D's will be one behind, so it'll be 40. So you go 5S, 40, 5P. So D's are one behind, and then the F's are a second behind. So F's are going to be, if this is 58, it actually shows up right here. So even though I'm at 1, 2, 3, 4, 5, 6, the sixth period, I'll go 6S, and then I'll jump down and fill these up. They're 2 behind, so 4F. I'll come back to the D's. This will be 5D, right, because we said 3D, 40, 5D, and then this is back to 6P. Okay, so continuing. I just did 4S2. I'm now at 3D. I don't remember how many electrons fit on the 3D, so I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That makes sense because we said there were 4 flowers and a donut. There's 5 different orbitals. Every orbital can hold 2 electrons. So on the D sub level, you can hold 10 electrons. So I'm to here. I need to get to here. So I'm on the fourth level. I'm in the P subshell. I'm going to place 1, 2, 3, 4 electrons there. 4P4, and then I'm done. So for the potassium ion, first I want to know how many electrons that thing's going to have. So here's potassium. Potassium has 1 valence electron. It's an alkali. So when it forms a charge, when it becomes an ion, it's going to lose that outermost electron. It's kind of like if it looked like that. It just had this 1 electron. It's going to lose the outermost electron to get a full shell. So instead of 19, it's going to have 18 electrons. So for the potassium ion, I described the first 18 electrons. They always start the same. So this is 1s2. Now I'm down here, 2s2, filled those out. Now 2p6 to fill those out. Second shell, p orbital, 6 electrons fit. Now I'm here, third shell, s subshell, 2 electrons fit. Still the third shell, p region, and I'm going to place 6 electrons. 3p6. And I stopped there because I took one of potassium's electrons off to make it an ion. For the last one, I have chloride. For the chloride ion, I know chloride is right here, tends to gain 1 electron, so instead of 17 it has 18. It's going to have the exact same electron configuration. So what that tells me is that when potassium and chloride both form ions, their electrons are arranged the same way, and that happens to be the same way that argon is arranged, a noble gas. Okay, so energy level / period on the table, subshell / columns in the table, so section in the table, and number of electrons or boxes that there are. All right. So there's another way to describe where electrons are located, and I think we need